We are in the middle of global health crisis. As the risk of diabetes and obesity continue to escalate worldwide, health authorities are pointing to a major culprit, our overconsumption of traditional high glycemic sugars. But what exactly happens when we eat sugars? In the small intestine, high glycemic sugars are broken down rapidly, triggering sharp spikes in blood glucose. To compensate, our pancreas is forced to release a massive wave of insulin, a relentless cycle that exacerbates metabolic disorders over time. So, how do we keep the joy of sweet foods without the dangerous metabolic consequence? In the isomalt is a natural source sugar substitute with only half the calories of table sugar, just 2 kilocalories per gram. Let's explore how this unique ingredient is reshaping the future of diabetes-friendly nutrition.
To understand isomalt, we must first look at its starting point, which is standard sucrose, with the chemical formula of C12H22 or 11. As you can see in the chemical structure on the screen, this common disaccharide serves as the foundational building block for the complex sugar alcohol we are about to explore. In this slide, we will go through the 2D Howard projection of GPM and GPS. A critical point to understand is that isomer is not actually a single molecule. Instead, the hydrogenation process naturally resolves into a stable mixture of two distinct molecular parts. These are GPM or 1,0-alpha-D glucopyranosyl D-mannitol dihydrate and GPS known as 6,0-alpha-D glucopyranosyl D-sorbitol. This slide illustrates their 2D Howard projections, highlighting the specific structural arrangements that give isomer its unique functional characteristics. How do we move from simple sucrose to this dual molecule mixture? It is a specialized two-step synthesis pathway. Step 1 involves an enzymatic rearrangement, where an enzyme rearranges the sucrose molecule into an intermediate compound called isomaltulose. Step 2 is catalytic hydrogenation using hydrogen gas and a Raney-Nickel catalyst. This second step reduces the fructose portion, finalizing the conversion into the stable GPM and GPS mixture we see here. To reinforce this process, the transformation is a deliberate two-step chemical evolution. By utilizing enzymatic precision followed by catalytic reduction, we effectively alter the sugar's bond structure to create a product that behaves very differently from standard table sugar in both the lab and the body. Isomer is officially classified as a sugar alcohol or polyol. This classification is driven by the clusters of hydroxyl groups mapped along its carbon chain, as shown in this ball and stick model. Because of this signature, isomer offers a clean, sweet taste without the typical sugar rush. Its relative sweetness is approximately 45 to 65% of standard sucrose, and notably, it lacks the strong cooling aftertaste common to other bulk polyols. Now that we have established the chemical who and how, I would like to transition into the specific physical and functional properties that make isomer a superior choice for various applications, particularly regarding stability and shelf life. One of isomer's most impressive features is its low hygroscopicity, which I like to call the moisture shield. While regular sugar is highly hygroscopic, meaning it absorbs moisture from the air and becomes sticky, isomer absorbs almost no moisture. It remains dry and stable even in humid conditions. This high moisture resistance, combined with heat stability, is what allows manufactured goods to have a drastically extended shelf life. This table summarizes my findings by connecting microscopic chemistry to macroscopic properties. Strong linking bonds allow isomer to resist digestive enzymes, resulting in a low calorie profile. The abundant hydroxyl groups define it as a polyol, providing that clean sweetness. Finally, the dual GPM-GPS molecular matrix creates the extremely low hygroscopicity that ensures products remain non-sticky.
Alright, now let's move on to the next part, which is looking at the particle application and how isomer actually kicks in inside our body. First of all, because isomer is highly resistant to moisture and doesn't get sticky easily, it's honestly a premier ingredient in the food industry right now. Manufacturers love using it for things like hard candy, chewing gums, and sugar-free chocolates. It gives the exact same bulk and texture as regular sugar, but makes the product last way longer than on the shelf. Another really cool thing is that the whole production site is moving toward green chemistry. So instead of heavy chemical processing, factories are switching to eco-friendly extraction and using renewable energy to keep their environmental footprint as low as possible. But as chemistry student, the coolest part is how it reacts psychologically. Remember those strong chemical bonds we just looked at the structure slide? Because of those unique, our body takes about 11 times longer to break down isomalt compared to table sugar. That's why its glycemic index is super low, around 9, meaning it completely eliminates those dangerous blood sugar and insulin spikes. It's totally game changer for managing diabetes. On top of that, isomalt is non-carcinogenic, meaning it's totally tooth-friendly since mouth bacteria can turn into cavity-causing acids. It also passes through to the stomach intact, acting as a great dietary fiber once it hits the colon. But a quick head up, don't overdo it. Having more than 50 grams a day can trigger heavy gut fermentation and water retention, leading to bloating or laxative. So mandatory is a key.
Scientific research consistently support these benefits. Clinical studies show that replacing sugar with isomalt significantly lower postprandial glucose and insulin response. Furthermore, isomalt acts as a prebiotic in our digestive tract, feeding the beneficial bacteria in our gut and supporting overall digestive health. The science backing Isomalt metabolic benefit is stronger than ever. A 2024 randomized controlled trial published in NutraFood investigate that the real-world impact of replacing sugar with Isomalt across everyday sweets like candies, mints, jams, and chocolate. The findings were nothing short of a breakthrough. The study revealed that substituting sugar with isomalt drastically reduced the 2 hours postprandial blood glucose response by an impressive 61% to 71% depending on the confections. Even more importantly, the corresponding insulin peak was significantly blunted by 70% to 92%. Think about that. The same sweet indulgence, but with up to 92% reduction in the body insulin burden. This recent clinical advance confirmed that by integrating isomalt into modern food formulation, we can successfully balance our love for sweet with the critical glucose control. In conclusion, Isomalt proved that we do not have to sacrifice sweetness to protect our health. By making smarter choice in the sweetener we use, we can take a massive step forward in the fighting the global diabetic crisis. Thank you so much for your time and let's work towards a healthier, sweeter future.